Hi, Mick McQuaid here, welcoming you to day 8 of iste780, Data-Driven Knowledge Discovery, the last day of week 2 as we race along here. And today's topic is going to be a lab. We're going to do a lab on logistic regression, linear discriminant analysis, quadratic discriminant analysis, and k-nearest neighbors. And we're going to do this using the stock market data set, and then we will also do an application to some insurance data. And of course, today your assignment is an application-oriented assignment that's very much based on today's lab, based on the techniques that we'll do in today's lab. So let's begin. Now I'm going to lay things out a little bit differently than I have been because I've got something I've got some results today that demand a slightly wider output. So I've been playing around with different outputs. Let me turn on R here, which of course opens in a different window. And I think this will about serve the purpose. We shall see. Something I obviously should have done before I started. Sorry about that. Okay, and then we're going to use the ISLR library. So the first thing we want to do is load that library, which presumably we've downloaded previously. If we haven't downloaded and haven't installed it, we'll get an error message when we do this. And then I'm going to include a couple of options. Let's see, I'm going to set width equal to 90. Let's see how that works out. And digits, I'm going to set to 3. And that's just to match the output that you see in the textbook for this lab. Okay, so let's take a look at the stock market data, which, as I said, is part of the ISLR library. So once we've loaded the ISLR library, we can look at the stock market data. So what are the names of the columns in the stock market data? Here they are. What are the dimensions of the stock market data? Here they are. And what is a summary of the stock market data? Here it is. And, okay, I don't know if that's going to be wide enough. The next thing actually is a pairwise comparison. And this is the scatter plot matrix that we've done before, which of course is opening in a different window. And if I put it in this window, you're going to see it's kind of a mess. Enlarge it so you can see a couple, but there's not really much of a difference between these and the others that you're not seeing. It's there's a lot going on, so much going on that we can't see patterns in this. We can't easily see patterns anyway in this data. And if there are patterns, they're very limited patterns. Okay, and then here's the correlation matrix for stock market data. And we get an error message when we try to do that. X must be numeric. So I'm going to have to say the stock market data minus column 9, which is not numeric. So I'm saying every row there, and I'm saying not column 9. Oh, that is wide enough. Okay, good. That was what I was concerned about, was that it would be wide enough. So there's a typical correlation matrix. And this is just like a covariance matrix. We talked yesterday about covariance matrices. And the only difference between the correlation matrix and the covariance matrix is that the correlation matrix is scaled. So you see that instead of the variance on the main diagonal, we see ones along the main diagonal because the covariance is, I mean, the correlation of a data set is, the correlation of a vector with itself is always 1. Okay, now let's see, what else do we have to do to describe this? Oh, let's attach the stock market data. So this will prevent us from having to always refer to the columns with the word S market and a $sign in front of them. And let's plot volume. And so we see volume increases over time. So this index is trading days. Okay, so the first technique that we're going to do with this is going to be logistic regression. So the way that we do logistic, so let me just put a little note in there in case you want to return to this file. And we'll call our logistic regression object GLM fit, and we'll create that object with using the GLM function, and we're going to use direction as the response. So the direction is up or down. So the stock market market as a whole moves up or down, or whatever index we're looking at moves up or down each day. And then we're going to look at yesterday's performance, the day before yesterday's performance, the day before that's performance, the day before that's performance, the day before that's performance, and volume. Trading volume. So these are our typical things to look at. I'm not convinced that we need to say data equals S market. It may very well be that we need that if we've attached more than one. So, some R functions require it, some don't. Okay, so we've created that object, and now we can take a look at a summary of that object. And the summary of the object tells us that, ooh, doesn't look like a pretty picture at all. Notice that these p-values, for the most part, are extremely large. We're not able to explain the direction of the market with its performance yesterday, yesterday, the day before, or the day before, basically for the past business week. But the best p-value here is lag 1. That's still not good. This is certainly, you're not going to make a fortune in the stock market using this technique. But it does. But it's you know, it's kind of a textbook exercise here. Okay, so let's see. So that was okay, so now we can access just the coefficients with this. So this is just getting us familiar with how the machinery of this works. So here are the coefficients, and if you take a look at the first column above that says estimate, that's the same information that we just got here. Another way that we can get coefficients is to say, let's see, summary GM fit coef, and that gives us the entire table of coefficients. And if we just want the fourth column of that, or some column of that table, that's shown to us as well. You can just go like that, and you'll notice that these are the p-values. So this is this column right here. It's the result of selecting just the fourth column. So, and you may want to select these, you know, you may want to select pieces of an object for further processing. That's the main reason for doing this, is that it's often going to be the case that in practical usage, you want to chain a bunch of things together. So you want to be able to name different parts of each object that you use. Excuse me. Okay, so let's take a look. Let's use the predict function here to predict the probability that the market will go up. And don't get too excited. We're not gonna. We don't have a very good chance of predicting this. Don't get too excited. What am I saying? Okay, so we're predicting taking the logistic regression object as our input. And then let's take a look at 1 through 10. And these are the probabilities of going up rather than going down, because we can tell by doing contrasts that R has created an indicator variable with a 1 for up. So this is the probability of going up. Okay, so this is it's just the oops, wait a minute, I'm doing this in the wrong place, aren't I? Oh. So I've changed how I lay out the screen, but I haven't acclimated to it yet. Now I'm making all kinds of mistakes here. There we go. There we go. So you can see by doing contrasts that R is using a 1 for up. So that means that these are the probabilities of going up. Okay, so if we want to make a prediction, we're going to convert these into labels like up or down. So let's do that now. So we're going to make a vector of predictions. And first we're just going to repeat. We have 1,250 rows, I think. So we're going to create 1,250 predictions of down. And then we're going to say that any place where GLM probs is greater than 5, we're going to give it up. So they all start out as down, but then any ones like these, for example, this or this, for example, any of these now have been switched to up. So we have this vector glm.pred that contains ups and downs based on these probabilities now. And so let's tabulate this. Okay, and then we can, so this is the confusion matrix. And this is something that you're required to produce in the homework, so you should know how to do this. We'll do this several times. And we can either manually check the probability. So what we want to do is find out the probability of a correct prediction here. So that is the predictions along the diagonal, which would be 507 plus 145 divided by the total. Is that the total? 1250, I think so. Now we can also get this same information by just asking. The mean for direction. We can also get the mean for not some value of direction. So we get the same results here. Now that's funny. I'm getting 3 places after the decimal point. I thought that, okay, whatever. So this doesn't exactly match what I was expecting to get. Let me just change the options to 4 here. So earlier when I was doing this, I was getting, let's see what happens here. Okay, so now I'm matching there. Okay. This matches the textbook output. So what we would like to know, so we haven't, we're using the training data, and then we're seeing how good we did with the training data, seeing how well we did with the training data, which is not a good strategy. What we need to do is have training data and test data. So let's create a training data vector from before the year 2005, and then a test vector from the year 2005. So train is going to be just this expression year less than 2005. So this is just, so this object is just a Boolean expression. And now I'm going to say that smarket.2005 gets smarket where the rows are not train, and the columns are just all of the columns. Okay, so now I have a training data set that's everything from before 2005. And what is the size of that? Well, let us see. (252 by 9). Okay, and then we're going to say that the direction 2005 is going to be direction that's not a training set. Okay, so this is our set of data from 2005. This is going to be our test set. I think I just before said that it was going to be the training set, but exclamation point train means not train. So this is going to be our 2005 is going to be our test set, and the stuff from before that will be the training set. Okay, so now let's do a logistic regression. Just did one, so this is just the same thing. In fact, I probably should just copy and paste from above instead of typing it out again. Sorry to bore you with my excessive typing, but I actually sometimes prefer to type, because sometimes when I cut and paste, I don't notice something about what I'm doing, whereas if I type it in, I tend to look at every single detail, and then I'm able to question it if there's if I see some problem or something seems to be amiss. Okay, so the subset train is, oops, I can't do that. Oh no, that's a real problem. I just tried to create an object called GLM, and what I meant to do was, I don't know if that's, I may have made a serious blunder. I might have to reload the library. I don't know. Let's see what happens. This will be interesting for me. So you shouldn't be able to create an object that masks an existing R object, but maybe I can, and maybe I just did. Okay, so now I'm just going to create a vector of down that's 252. Oops, 252 elements long. And then I'm going to do exactly the same thing that I did before. Give it up. Give it up. Okay, now let's see. Now comes the moment of truth. And it works. Okay, so I was not able to overwrite an R object with a dopey thing of my own. So it's okay to make some mistakes. Okay, so let's take a look at the mean of this. We can do this manually the way we did before, or we can ask R the question. And R tells us that. And let's look at not equals. Okay, so here's equal to and not equal to. So the last command is telling us the test set error rate. And the test set error rate is worse than actually random guessing. So even though our training set looked like it might not be too bad, it really was bad when we applied it to some test data. Now, and the authors make the wry remark that if this were a good model, they would be out making a fortune on the stock market rather than writing textbooks. And indeed, if the stock market were easy to gain, that market would be over. Vultures would have swooped in on it already and cleaned it out. Actually, there are vultures there cleaning it out, but they use insider knowledge, I guess. Okay, so let's do this with. Here, I'm going to cut and paste this one because I think I'm doing the exact same thing except cutting out a bunch of the data. So let me just see here. Train. So all I'm going to do here is cut out all of this junk. Just use lag 1 and 2 and see what that does for us. And then I would like to do the same things that I just did. So I want to do that again. And I want to do that again. That again. Actually, I didn't need to do that first one again. Table again. Mean again. And what is this? Oh, so this is the, so, okay, so here is a an interesting issue here. So what we're looking at here is yeah, so the 56%, we have 56% correct predictions. However, if we had, because the market increases that much of the time, if we simply predict that the market will increase every day, we'll get that same number. So in terms of using logistic regression instead of just standing around, doing nothing with any sense to it, there's no advantage to applying logistic regression to this. However, on days, okay, so when we predict, so what is this? Days when we predict up. Oh, okay, I see what they're getting at here. Let's just let me just add this in here. So here are days when we predict up. We're right 50%, 58% of the time. So if we could use the strategy of only buying on days when the model predicts an increase, and avoid trading on days when a decrease is predicted, we would do better than a naive strategy. And of course, they make the, I think, slightly tongue-in-cheek comment that we would need to investigate whether this was real or just due to random chance. If it is real, people have already taken advantage of it and squeezed it out of the market. There are specialists who are called technical specialists in the stock market who try to use patterns exclusively to trade, and during times of bull markets, they seem to be doing well, but they don't. Their methods are, how shall we say, not robust in the face of a downturn, whereas the other kinds of specialists who rely on what are called fundamentals, which would include people like Warren Buffett, seem to be successful during periods of downturn also. All right, let's move on to linear discriminant analysis rather than talking about the background of the stock market data. So this is in a different library. And there's also, so this has got an LDA that's in the library mass. We're going to have to put in here. There's also LDA that I mentioned yesterday that stands for something completely different, but is in a different library. In fact, there are, I think, multiple LDAs in different libraries that mean different things. Mass is one of the most frequently, at least in my experience, one of the most frequently used libraries. Okay, so we're going to create a linear discriminant analysis fit object by doing the linear discriminant analysis function on just those first two. And if we just state that, we'll see a summary of it. And we can do a plot of it. And we find that what is it, 49% of the training observations correspond to days during which the market went down, and 50.8% correspond to up. And we also have gotten group means here, the average of each predictor within each class, suggesting that there's a tendency for the previous two returns days to be negative on days when the market increases. And the coefficients of linear discriminants output provides the linear combination of lag 1 and lag 2 that are used to form the LDA decision rule. So this is what forms the discriminant. It's the small Greek delta in the text. Okay, and then we can do what else? Predict. And this provides us with three objects. So let's take a look at what the names of those three objects are. Okay, and predictions are going to be almost the same. So just for convenience, we're going to put this into something that we can reuse. We're going to tabulate the class. Oh, now that's funny. I could swear I just created that object, didn't I? Did I make a mistake when I created it? I'm just not really seeing the error here. Did I not do this? Oh, I typed this in, but I didn't actually do it. Is that right? Yeah. Okay. Okay, it's mid-afternoon as I'm recording this, and I'm ready for another cup of coffee. Okay, let us push on, though. I'm sure that you are as much in need of coffee as I am, if not more so. Okay, I don't want to peddle my stimulants on you. Actually, you know what? I'm going to pause this. Okay, you may have heard a crackle there because I paused. Let me get back here. And let's find out the mean here. And the mean is about 56. Now, okay, so this is so strange. They've changed. I'm going to change my options back to 3. So at some point in the course of doing this, they changed their options. And at some point in the course of creating the lab, I should say, the authors changed their defaults. Okay, so now what we would like to do is recreate the predictions that are contained in class. So we're going to apply a 50% threshold. So you may recall that 50% threshold isn't necessarily ideal from the point of view of whoever is doing this. That's ideal from the point of view of classification. And so those should sum to 252. Okay, now the posterior probability output corresponds to the probability that the market will decrease, actually. So let's look at the probabilities, and then let's look at the words. You can see that this corresponds. So you can see that wherever it's below 50%, we've chosen up, and wherever it's above 50%, we've chosen down. It's a little too wide for comfort here. I'm going to change, let's see. That looks a little bit better. Ah, much better. Okay. Alrighty then. So we might prefer to not use 50%. So let's suppose, for example, we would like to use 90%. Let's say greater than 0.9. And guess what? There's nothing. There are no days that meet that. There's no days with that probability. As a matter of fact, the largest probability that we get is about 52%. Okay, so enough of this. Let us move on to yet another model, which is quadratic discriminant analysis. My computer is overheating. I don't know if you can hear the fan. It doesn't seem like I'm doing much right now, but for some reason I'm getting wild fan and CPU temperature readings. Maybe it's some malware busy chewing up cycles, but I don't think it's R. Okay, so let's create a quadratic discriminant analysis fit. This is in the same library, so we don't have to do a new library. And we do this with the quadratic discriminant analysis function, the QDA function. And we're again going to use the two that seem most promising, lab1 and lab2. What do I want to say lab1 and lab2? Data equals S market. Subset equals train. And as with LDA fit, we can just look at this. We don't have to say summary to get what's going on here. Okay, so we see some output here, but not all of the output. And we can use the predict function the same as we did in LDA. So I'm going to do exactly what I did in LDA. Now I'm going to just type this. You can, if you want to just go back up and cut and paste it, that's fine with me. Doesn't matter that much. I tend to more easily remember what I did. Oops, I cannot type and talk at the same time now. It's not very well. So this is what we did before, except that I didn't. What did I do? Oh, QDAT instead of QDA fit. Okay, there we go. So I don't mind if you cut and paste a lot. It's a good way to avoid errors, in fact, just as you saw there. As I'm trying to talk and type at the same time, I have a tendency to make a lot more errors. But I tend to remember what went on better. There is some research that actually claims that you don't remember what you type, that you should actually handwrite things if you want to remember them, that there's some sort of body memory that's associated with handwriting that's not associated with typing. But I don't know the circumstances of that research. I don't know how narrowly that research was cast. And until I do, I'm pretty set in my ways. I like to. No, I say that and I make a mistake with every single keystroke. Okay. Okay, and ooh, this is very promising compared to LDA. So maybe there's something going on that a pattern that we can capture, but that the pattern is just more complicated than a linear model can catch. Of course, don't bet your savings on this. It's probably not going to work on the stock market as a whole. If you really want to invest in the stock market, it's more than a full-time job. If you want to be successful, it's more than a full-time job. Okay, now let's move on to yet another technique. K nearest neighbors. And for this one, we're going to use a different library. And I am not sure whether this library actually comes with R or whether I installed it, whether it's part of the base or whether I installed it. I'm not sure if you have to download this or not. It's always worthwhile to check for, to check the package installer. And the reason for that is that again, I have this problem of not being able to type while I talk. The reason is that with the package installer, you can update your installed packages as well as installing new packages. And bugs are often found and fixed. That's one of the advantages of ours, that there's a very active community finding problems and correcting them. Well, I should have just used that. Oh, well, I should have cut. There's a case where I should have cut and pasted. Okay, so this is what's not, so the test set is what's not in the training set. Okay, and as I mentioned before, it's okay to use this symbol that I keep using, except in inside parameter lists. Well, this isn't an assignment statement anyway. This is an equal sign. This is the mathematical equal sign, but there are some other ones where you'll see that I've said use the equal sign instead of that operator that's the less than sign followed by the hyphen. Okay, so where are we? Oh, okay. So now, before we apply k-nearest neighbors, what we would like to do is set a seed so that we can reproduce this. So you don't really have to do this. If you want the same results as are in the textbook, you have to do it. And if you want to be able to reproduce your results exactly, you have to do it. But you don't have to do it for k-nearest neighbors to work. It's just a convention to be able to find spot errors and stuff by using the exact stuff. In fact, that's one of the main reasons for doing the lab from the book, is so you can spot errors and see what you're doing before you actually have to do it by yourself. Okay, so I've created now the KNN predictions. Let's take a look. And not good. Okay, so let's take a look at the mean here. Oh, here they're doing it manually, but I should be getting the same results. Yeah, I get the same results as if I did it manually. So when I say they're doing it manually, I mean they're adding up the main diagonal and dividing by the total size of the set, which is 252. Okay, now it could be, they mentioned that it could be the case that k equals 1 is the problem. So let's try it with k equals 3 and see what happens. And we're just going to do the same thing over again. Table. And we get an improvement. However, they're going to tell us that that improvement is as much as we're going to get. If we go to k equals 5 and k equals 9 or so on, we're not going to get any more improvement out of it. So the results so far show that in this particular case, quadratic discriminant analysis did the best job. Okay, now let's move on to the caravan data. This is the caravan insurance data, and I'm not totally clear on what they mean by this. I think that it is what in the United States is called mobile home insurance or travel trailer insurance. And it is in the ISLR data set, so we should be able to just say dimensions of caravan, and yes, it is. And this is 5,822 potential customers for this kind of insurance. Not many of them actually have bought it, so let's take a look at that. Let's attach it. And let us do summary of purchase. So this variable is whether or not they purchased the insurance. And we see that far fewer purchased than did not purchase. And so the fraction that have purchased, we can just say 348 divided by 5474 plus 348 tells us that only 6% or so have bought it. All right, now there is a problem with this data, which is that we have variables like salary and age. So we have salary measured in dollars and age measured in years. What if we measured salary in Japanese yen, or if we measured age in minutes? We would get very different classification results from what we get if these variables are measured in dollars and years. So an idea to solve this problem is to standardize data so that all the variables have a mean of 0 and a standard deviation of 1, and then all variables will be on a comparable scale. So this is a really handy function because it will just do the whole thing at once. So let's call this standardized. We're calling it standardized X is going to get scale caravan, except we do not want to standardize purchase. Did I do that wrong? Yes, I did that wrong. Is that now correct? Yes, that's not correct. Okay. Now, if we take a look at the variance of, say, column 1, so there's the variance of column 1, caravan, column 1, we get, oh, wait a minute, I made a mistake on my previous. Okay, so the variance of column 1 is 165, but suppose that we check the variance for column 1 of standardized X. It has variance of 1, so of course it has the standard deviation is the square root of the variance, so of course it also has standard deviation of 1. And so do all the columns. So if we do the same thing with column 2, oops, what did I just do? That's what I was trying to do. So if we do the same exact exercise with column 2, we get this 0.165 for column 2 of caravan, and 1 for column 2 of standardized.x. Okay, now let's split the observations into a test set and training set the way we did previously. So the test set will be the first 1,000 observations. So test is going to just be the sequence of numbers from 1 to 1,000. And train.x is going to be standardized.x minus test. So this is all the rows that are not in the test set. So that means all rows other than rows 1 to 1,000. And test, we may as well just reuse this. Test is going to get all the ones that are test, meaning all the ones that are 1 to 1,000. And the training data set is going to get just this one column. So this is the response column. It's going to be not test. And test y, I may as well do the same thing here. Test y is going to get purchase test. Did I do that right? No, I didn't do that. I didn't do the training one, did I? Okay, I think I've got them all now. Okay, and then we'll set a seed to make it the same as the textbook. And now we'll create k-nearest neighbors predictions. And we'll do it once again with the very unpromising k equals 1. And so this is our error rate. And this is our error. Oh, okay. So, so our error rate is almost 12%, but only 6% of our customers purchased insurance. So that's very sad. So this is the fraction that did not say no to the purchasing of insurance. So sorry about that. It would have been probably better to say mean test y. Let me just do that. I think that. Yeah, so I just think that is easier to read. Okay, so that's a problem. So this is a problem that we've encountered, analogous to problems that we've encountered before. Only 6% of customers purchased insurance, so we could get the error rate down to 6% by always predicting no, no matter what the value of the predictor. So this is one of those cases where we're really only interested in a very small fraction. We're not interested in reducing the error rate overall. We're really only interested in some much smaller error rate. So let's suppose that it, and it does, let's suppose that it costs money to sell insurance, that the insurance company has to send out a salesperson for each potential customer. And if the company just sends the agent out to a random customer, then the success rate will be about 6%. So that's what we expect overall. You know, there'll obviously be variations in the quality of the salespeople and other factors, but overall, based on what we know, we're going to guess 6. We were expecting 6%. So the overall error rate is not what's interesting. What's interesting is who are correctly predicted to buy insurance. And KNN with k equals 1 is actually quite a bit better. So let's take a look at the confusion matrix here. And what we're going to see is that we get about 11%. We correctly predicted 11% purchasing insurance. So so this is better than just randomly sending them out. If we send out, in other words, if we send the insurance agent only to those that we predict will purchase, 11% of those will purchase. And the equation that they do, or the not equation, the expression that they do for that is the bottom row of the table. So that's the bottom row of the confusion matrix is the fraction correctly predicted over the fraction predicted to purchase, and that result is 11%. So that's twice as good as random guessing. So we only want to send them out to these guys. Now, if we just make the small change of switching to k equals 3, we're going to do a little bit better than that. So here we're going to say 5 divided by 21 plus 5. We get about 19, a little better than 19%. What if we do k equals 5? Will it be even better? Let's try that. And now we have 4 divided by 11 plus 4. 26%. This is starting to look like good business. Okay, now, so k nearest neighbors did pretty well on this. So now a question is, would one of the other methods do well on this? So let's try, and this is actually the last thing to do, is to just quickly try logistic regression. And, you know, I hate to give away spoiler, but that's to do with logistic regression. It's going to be better. Okay, so we're going to create the GLM fit object as we did previously. And this is with the training data. The subset equals minus test. And we get a warning message, but we can continue. It's not a big problem. And then we were going to say GLM, this is exactly what we did previously. And then probs are going to get predict GLM fit. And then test type equals. So we're taking the training data and we're using it to predict. We're taking the test data, excuse me, and we're using it to predict based on the model we developed with the training data. Sorry, I see that backwards. Okay, and then let's see. I'm going to create a vector of 1,000 no's. GLM thread is going to get no, 1,000 times no. And then we're going to substitute yeses for all of those. Whenever we're above 0.5. So now we're going to have a vector of yeses and nos. And now we can table that. Ooh. Let's try 25%. Did not do well. Okay, so let's see, GLM thread. We get. Oh, okay, so I'm going to have to do this over again. And I'm going to do this. Now I can table this. And yay! The results are good. 11 divided by 22 plus 11 probably. So without calculating it is 1/3. So 1/3 is better than 26%. So 1/3 beats. So logistic regression actually beats the nearest neighbor here. But it won't always be the case. All right, well, that's it for this lab. Now time to move on to the homework. Thank you for your attention, and thank you for completing week 2.